Okay, let's say we have a problem like this where there are two masses. One is a 35,000 kilogram mass, the other is a 10,000 kilogram mass, and this is located at the position of 0, and this is 2 meters as its position, which means it's 2 meters away from this mass. So I'm going to call this M1 and M2 for, just to make things a little easier. And we have to find where we should put some third mass, M3, so that the the net gravitational force is 0. So here's what you do. You choose a location for M3, and I'm going to just randomly choose that it'll be there, right? And if I'm wrong, if that turns out to be the wrong location, then my answer will tell me that. Now from here to here is 2 meters, right? So that's the distance separating these three masses. And here's my third mass, M3. Now, because this has mass, and because this has mass, M1 pulls on M3, and in fact, M1 pulls M3 toward it, to the left. So I'll call that force 1. And because M2 has mass and M3 has mass, M2 pulls on M3, and of course M2 pulls it this way. And I'll call that the force F2. Now, F1 and F2 are both gravitational forces, so each of these is equal to, we can use the equation Newton gave us, which is G times the two masses, the product of the masses, divided by the distance between them squared. So we're going to use this to find F1 and F2. But here's the clever thing about this problem. This problem is saying find the location, right? Find the location of M3 such that these two forces, F1 and F2, cancel out. In other words, they're saying find the location such that F1 is equal to F2, because then they point in opposite directions and they perfectly cancel. If F1 comes out to 10 newtons, F2 is 10 newtons in the other way, the other direction. So this would be negative 10 plus 10, they go to 0. So they're equal in magnitude, which means we could plug in on the left side Newton's equation, and then on the right side for F2 we could plug in Newton's equation. So let's see what that does. On the left side I plug in G M over R squared, and on the right side I plug in G, my R squared, G M over R squared, and on the left this is for force 1 that I've plugged in, F1. So force 1 is the force of mass 1 on my third mass. So the masses I plug in on the left are M1 and M3. On the right, over here, I have F2, and of course F2 is the force of mass 2 on M3. So I need to plug in M2 and M3 here. Looking at this, you see that the masses cancel, M3, they cancel out because there's an M3 on the left and there's an M3 on the right. But there's a problem here. I've just put R down in both the left and right side, but they're different values of R. So I should distinguish as R1 and distinguish this as R2. And of course R1 is the distance between M1 and M3, so this is R1. R2 is the distance between M2 and M3, so this is R2. So let me draw this into the picture. R1 and R2. And looking at this, we see that R1 plus R2 is equal to 2 meters, right? So we're trying to find the position where the third mass should be placed so that this is true, or so that this is true, right? And of course, if you look at this equation, another thing you can do to make it easier on yourself, the g's cancel, don't they? The g's cancel. And all we have then is M1 over R1 squared equals M2 over r2 squared. But I'm going to make life a little bit easier. Well, not easier. In order to solve for this problem, what they're asking us to find is r1, right? That's what we're trying to find, which means that we're going to have to get rid of r2 right here and replace it with 2 minus r1. So from this step, this line to this line, if you subtract r1 from both sides, you see that r2 is equal to 2 minus r1. And so if I plug in 2 minus r1 right here, now I know the mass m1, I know the mass m2, and I can solve for r1, which is the only remaining unknown in this equation. So from here, we could say that m1, which is 35,000, times 2 minus r1 squared equals m2, which is 10,000, times r1 squared, like that. Now I'm going to erase a little bit and keep going. I'm actually going to move to the next slide, and I'm going to solve on the next slide this equation. I'm going to solve for r1. So here's my equation which I'm solving. The first thing I'm going to do is, oops, I'm missing a 0 here. First thing I'm going to do is divide both sides by 35,000, and then I get 10 over 35 r1 squared on the right, like that. And now I am going to distribute. I'm going to break this out into separate terms. And of course, if we ever have a minus b squared, then we can rewrite this as a squared minus 2ab plus b squared. So I'm going to write this on the next line where a is equal to 2 and b is r1. So here's that step. I have 4 minus 2 times r1 plus r1 squared. Oops, that's a squared. And that's my left side of the equation now. And then on the right side, what do I have? I have 10 over 35, and that can be simplified as 2 over 7, r1 squared. So on the left now I just have, let's see, 4 minus 4 r1 plus r1 squared, and I'm going to subtract 2/7 r1 squared from both sides. So I've just taken this now and moved it over to the left side of the equation by subtracting it from both sides. And now I'm going to put all of my r1 squared. I'm going to put all the r1 squared terms first, and then the r1s alone, and then the last thing 4. So I have r1 right here, r1 squared minus 2/7 r1 squared. So 1 minus 2/7 is 5/7 r1 squared. And then I'm subtracting 4 r1, and then plus 4 equals 0. So to solve this problem, we need to use the quadratic equation. Right? We have to use the quadratic equation. And the quadratic equation says the unknown, which is r1 in this case, is equal to, and let me write this a little bit lower. It says the unknown, r1, is equal to the opposite of b plus or minus the square root of b squared minus 4ac and then we divide all of this by 2a. So the funny thing about the quadratic equation is figuring out what A, B, and C are. Right? This is A. Here we have minus 4r1, but we really should write this as plus a negative 4r1. So negative 4 is B, this is A, this is B, and then here is C. So what I've just done is I've said I'm going to rewrite this equation in the form A times the unknown squared plus B times the unknown is equal to C. Oh, excuse me. Plus C is equal to 0. There we go. And I rewrote this equation to have this form so that I could figure out A, B, and C, the coefficients to the r1 squared, r1, and r to the 0 terms. Anyway, you just have to get it, you just have to make this equation look like this, and then you know what A, B, and C are, and then you can plug those values for A, B, and C into this equation. So for B, you put in negative 4, right? So minus negative 4 becomes positive 4, and then you do the equation once with plus, and you just take the square root of B squared, which is going to be 16, minus 4 times A is 5/7, times C, which is 4, and then you divide by 2 times A, right? So that'll be 10/7, 2A is 10/7. Then you do the same calculation with a negative sign right here instead of the plus. And what you get when you solve it this way, when you do these two solutions, is you get, okay, so what you get is, as the two solutions, because every quadratic equation yields two solutions, and in this case, we get 4.3 meters as R1, or 1.3 meters, right? So this is tricky because both of these solutions are real. Both are real. And we have to figure out which one is the true solution given the physical scenario that we're dealing with. So let's look at our picture again, and that will lead us to figure out which of these two solutions we must pick as the real answer. So in our picture, here was M1, here's M2, and this was located at the position of 0 meters, M2 is at 2 meters, right? Now, the two solutions that we have from the quadratic equation is that M3 is either at the position, it's either at 4.3 meters from 0 or 1.3 meters from 0. Now 1.3 meters would put it like about here, M3. And let's draw the forces, what they would look like. Well, M2 would pull it this way, and M1 would pull it this way. Right? That's what our force diagram would look like if M3 were located right here. On the other hand, if M3 were at 4.3 meters from 0, from this position, then that would put it all the way out here. M3, here's our other option. Here's the first possibility, here's the second, right? This is the second, this was the first. And if that's where M3 is, then is it in equilibrium? Do the two forces F1 and F2 cancel out? Well, F1 would pull it toward it. Mass 1 would pull this towards itself, towards mass 1. And mass 2 would pull M3 toward mass 2. So F1 and F2 could not possibly cancel out if M3, the mass, M3, our third mass, if it were located over here, there's no way these two forces cancel out. So 4.3 is not a viable solution. It doesn't make sense physically based on what we know about how the forces are supposed to be canceling in the problem. So we can discard that as the solution. That's not the right answer. The right answer is 1.3 meters because that's the only position from our two solutions, that's the only position where the forces F1 and F2 could cancel out. And what the problem said is find the position where those forces do cancel out, where the net gravitational force is 0. So 1.3 meters is our answer.